This video program was produced for those technicians who are starting to repair CLD players or are learning principles and basic technologies of laser discs and compact discs. This video is intended to explain the structure and functions of a CLD player. For more detailed explanation, please refer to the tuning fork. You should also refer to the video Tuning Fork Part 1, explaining overview of laser discs and compact discs. This video program is composed of 6 chapters. Components making up a CLD player and their roles, structure and function of the pickup, structure and function of the FTS servo, structure and function of the tilt servo, structure and function of the TBC servo, and operation of each servo while LD playing. The video is produced so that each chapter can be learned independently. You can select the chapter which you want to watch with the chapter search. A CLD player is made of pickup, FTS servo, tilt servo, and TBC servo. Video signal demodulation and processing section. Sound signal processing section. And power supply. This picture shows the components of CLD 1090. The pickup represents the most important component of a CLD player. It reads the projections with a laser beam. These projections are called pits and are recorded on the single layer in the disc. After reading pits, the pickup converts the optical information into an RF signal, which is an output for further processing. For reading pits correctly, FTS servo, tilt servo, and TBC servo are required to control the pickup and rotation of a disc. The FTS servo means focus servo, tracking servo, and slider servo. The TBC servo stands for the time base correction servo, and it consists of spindle servo and CCD servo. Now we will explain the outline of each servo. The role of the focus servo is to control the vertical position of the objective lens built in the pickup in such a manner so that the correct focus is obtained on the signal layer in the disc at all times, even though the layer raises and falls as the disc rotates. When the center hole of a disc is not perfectly centered, track deviations occur in and out along the radius of the disc. So the tracking servo enables the laser beam to follow the track with precision by moving the objective lens along the radius of the disc. The slider servo is responsible for moving the pickup itself in and out along the radius of the disc while the disc is played or searched. In order to cope with warped discs, the tilt servo controls the pickup's angle so that the laser beam always strikes to the disc perpendicularly and crosstalk does not appear on the screen. The spindle servo controls the spindle motor for rotating the disc at the same speed at which the disc was recorded. The reproduced video signal contains the jitter, which cannot be compensated by the spindle servo. Furthermore, the CCD servo reduces the jitter so that the reproduced video signal is as steady as possible. These servos are needed to read pits correctly. Next, we will explain the video signal demodulation, the video signal processing section, and the sound signal processing section. In the video signal processing section, first, the frequency modulated video signal is extracted from the RF signal by using a band pass filter. Secondly, this frequency modulated signal is demodulated to obtain the video signal. The video signal processing section handles such operations as color signal correction, video noise reduction, and on-screen display operations. The sound signal, which is contained in the RF signal, is demodulated in the sound signal processing section. The sound signal processing section is divided into an analog sound system and a digital sound system. The analog sound system demodulates analog sound, which is recorded by frequency modulation, and the digital sound system demodulates the EFM signal to produce an audio signal. Analog or digital signal is selected and output from the terminal. In this section, after explaining the principle of signal readout, we will explain the functions and the roles of the main optical components which make up the pickup, such as the semiconductor laser, grating, half mirror, objective lens, and OEIC. Signals are read from the disc based on differences in light intensity that result from the presence, absence of pits, the length of each pit, and the distances between pits. These variations are then converted into an electrical output signal. The laser beam, which is emitted from the pickup, have a wavelength of 780 nanometers, and its phase is coherent. When the laser beam strikes a signal layer without pits, it is reflected by the aluminum layer and then returns to the pickup with its entire signal in phase. When the laser beam strikes a pit, the light reflected from the signal layer decreases. Since the spot of the laser beam is larger than the width of the pit, the light is emitted around the pit as well as on the pit. So the light wave crest of the light reflected off the pit and the trough of the light reflected off the non-pitted surface overlap one another and cancel each other out. This phenomenon is called interference. Since the height of the pit is a quarter of the wavelength of the laser light, the reflected light from the pit becomes 180 degrees out of phase. At the same time, dispersion will also reduce the intensity of the light reflected back from the pit. The semiconductor lasers used in CLD players have a wavelength of 780 nanometers. The signal recorded on the disc is read from its intensity of the light. Since the laser power is affected by the surrounding temperature, the laser power must be kept at a constant level by using a photodetector as a monitor. A grating is a glass plate whose surface has a number of closely equidistant parallel grooves. When a laser beam passes through this grating, diffraction is occurred by the individual grooves, and the laser beam is split into some beams. The intensity of the 0th order beam is 70% of laser power, and the intensity of the plus first order and minus first order beams are 10%. A CLD player employs a 3-beam tracking servo system for reading on-disk signals. So these 3 split beams are used in a CLD player. A half mirror is a transparent glass plate with one side of the surface coated with a metal oxide of magnesium or titanium. The half mirror has both properties of reflecting half of the incident light and admitting the remaining half. The half mirror reflects the light from the laser diode to the disc while passing the light reflected off the disc back to the photodetector. The objective lens is one of the most important components of a pickup, and basically the quality of this lens will determine the overall performance of a player. The objective lens focuses the light beam to a tiny spot, approximately 1 micrometer across, to read the extremely small pits. The objective lens is mounted on 2 actuators, allowing movement in both the focus and tracking directions independently. The actuator consists of magnets and a coil. OEIC stands for Optoelectronics IC. The OEIC combines in a single package the photodetectors that convert optical signals into electronic signals and the amplifiers that amplify these signals. The aim of this integration is to enhance the signal-to-noise ratio of the signals sent out by the pickup by immediately amplifying extremely weak photoelectronic signals from the photodetector. The photodetector is responsible for sensing 3 laser beams: the 0th order beam, used for reading the recorded RF signals and for detecting focus errors, and the plus first order and minus first order beams for detecting tracking errors. Since the shape of the beam must be detected by the photodetectors to achieve focus error, the photodetector for receiving the 0th order beam is divided into 4 elements. The RF signal is also produced by the 0th order beam. The composition signal from B1 to B4 photodetectors is used for the RF signal. As you can see, the photodetectors are accommodated together with the photodetectors for detecting focus errors, tracking errors, and the RF signal, thus bringing the total count to 6. The focus, tracking, and slider servo are called FTS servo from each capital letter. To detect the presence or absence of minute pits, the focal point of the laser beam should be on the plane of the signal layer at all times. The focus servo moves the objective lens up and down to achieve focusing on the signal layer and to keep the distance between the signal layer and the objective lens at all times. When the focus servo needs to correct the position of the lens, it must correct immediately. So the focus servo requires positional information on the objective lens, or information on the distance of the focal point from the signal layer, as well as in-focus, out-of-focus information. The focusing scheme used in CLD Players is called astigmatic aberration. The focus servo can detect the distance between the beam's focal point and the disc's signal layer by detecting the shape of the beam spot formed on the photodetectors and correct the discrepancy. The photodetector is divided into 4 element photodetectors in order to determine the shape of the spot. With the output of the individual element detectors, a signal that can be expressed as B1 plus B3 minus B2 plus B4 is obtained. This signal is known as the focus error signal, and its voltage and levels are varied by the amount of the laser beam, which is radiated to each photodetector. When the distance between the disc and the objective lens is extended, the spot becomes an elongated oval shape in the direction of B2 and B4, and the focus error signal registers a negative voltage. The spot on the photodetector has a circular profile as the laser beam comes into focus on the disc's signal layer. At this time, the focus error signal registers 0 volts. When the distance is narrowed, the spot becomes an elongated oval shape in the direction of B1 and B3, and the focus error signal registers a positive voltage. This is the principle of the focus error detection. In the focus servo operation, the composition of signals of B1 to B4 is used, as well as the focus error detection. This signal is known as the focus sum signal. During the focus signal being obtained, a CLD player detects that a disc is existing, and at this time the focus servo loop is closed. A focus error signal can be obtained only when the signal layer is in close proximity to the focal point of the objective lens. The objective lens must be moved to a place where the focus servo becomes locked by the lens up generator. If the objective lens is forced to move towards the disc, the focus error signal would vary as you see. At this time, the focus sum signal is detected by the disc sensing circuit, and it is transmitted to the zero crossing detector as an FOK signal. The zero crossing detector detects the zero cross point at which the focus sum signal is obtained, and the focus error signal comes to a 0 volt point. Upon the detection of the zero cross point, the operation of the lens up generator is stopped and the focus loop switch is closed. Then the focus servo becomes locked. Under the focus loop switch being closed, the focus coil is driven to make the objective lens focus on the signal layer by the focus drive circuit. The focus balance circuit is employed to correct the optical components of the pickup. When the laser beam is focused on the signal layer, the focus balance circuit makes the focus error signal set 0 volts by giving the DC offset voltage to the focus error signal. The objective lens cannot properly respond to a signal containing higher frequency components over 2 kHz. A signal over 2 kHz would result in a damaged coil due to excessive heat. To prevent this, a protective circuit is employed to reduce the gain of such a signal containing higher frequency components over 2 kHz. For a more detailed explanation, please refer to the tuning fork. When the laser beam is locked on the signal layer, the spot of the laser beam needs to follow the track, which is the row of pits. The tracking servo detects the position of the spot of the laser beam and the track by keeping watch on the reflected light of the laser beam, and make the spot follow the track with precision by moving the objective lens of the pickup along the radius of the disc. To optically determine whether the laser beam is accurately following the track, the single laser beam output from the laser diode is split into 3 beams by a grating plate. With the 0th order beam in the middle, the plus first order and the minus first order beams strike the signal layer at a slight angle. When the 0th order beam is on the track of the pits, the plus first order and the minus first order beams sit halfway on the track, and they register the same intensity on the detectors. At this time, the difference in intensity between the photodetector A, which accepts plus first order beam, and photodetector C, which accepts the minus first order beam, becomes 0 volts. This AC signal is reflected to as a tracking error signal. By this tracking error signal, the amount of discrepancy between the 0th order beam and the track can be detected. When the 0th order beam deviates towards the inside of the disc, the plus first order beam strikes the track, causing the plus first order reflected light to decrease in intensity. On the other hand, the minus first order beam moves onto the flat area between tracks, and as a result, its reflected light increases in intensity. At this time, the tracking error signal becomes negative. Conversely, when an outward off-track excursion is made, the reflected light of the plus first order beam increases in intensity, while that of the minus first order beam falls off. At this time, the tracking error signal becomes positive. For this reason, the tracking servo drives the objective lens of the pickup in and out along the radius of the disc, so that the tracking error becomes 0. At this time, it also makes the spot of the 0th order beam follow to the track. In the actual circuit, first, the tracking error signal is equalized by the equalizer circuit. The equalizer tracking error signal undergoes the drive circuit. Then, the signal is supplied to the tracking coil to actuate the objective lens, so that the laser beam spot trace the track. If photodetector A and C have a different sensitivity of light, or the differential amplifier has a DC offset, the 0th order beam tends to deviate from the track of the pit stream. To solve this problem, the tracking balance variable resistance is provided and applies an appropriate DC voltage in one of the photodetectors. As we already explained, the plus first order and the minus first order beams strike the signal layer so that their spots sit halfway on the track. However, when the pickup is replaced, the plus first order and the minus first order beams are often out of the right position. For correcting this, the angle of the grating is adjusted so that the spots of the plus first order and minus first order beams sit halfway on the track. This is called grating adjustment. The tracking servo makes track jumps during a search or scan operation, in addition to keeping the main beam on the track during normal playback. However, in this video they are not explained, so please refer to the tuning fork. Since the range which the tracking servo covers by following the track is approximately 0.5 millimeters on the signal layer of the disc, tracking cannot be maintained by the tracking servo alone. Remember that the signal spirals from the inside to the outside of the disc. The slider servo is thus used to move the pickup itself towards the outside of the disc, so that the tracking servo can always follow the reproduced track. To control the slider servo, a signal of low frequency components contained in the tracking error signal is used. The slider motor is driven in such a manner that the objective lens is always in the middle of the lens's operating range. The error signal which is used in the slider servo is detected with a resistor connected in series with the tracking coil. This resistor converts the drive current into voltage, which is then passed through a low pass filter for the extraction of DC components. The slider servo operates together with the tracking servo during playback. During search or scan mode, the pickup is forcibly moved by the slider motor. The laser beam which reads out the signal is emitted in a direction perpendicular to the signal layer. If the laser beam is emitted onto a warped disc, the laser beam will strike the surface at an angle or slant, causing the signal on the adjacent track to be read. This is because the spot of the laser beam is widened due to the slanting angle of the beam. It is the job of the tilt servo to vary the tilt angle of the pickup so that the laser beam strikes the signal layer in a perpendicular manner. The angle which the laser beam strikes the signal layer is detected by a tilt sensor, which is mounted on the pickup, is used. This sensor is made up of one LED and two photodetectors. Light emitted by the LED is reflected off the surface of the disc, and this reflected light then enters the two photodetectors. The difference of two lights entering the two photodetectors is detected as a tilt error signal. When the amount of light sensed by the two photodetectors is identical, the disc and the tilt sensor are determined to be parallel to each other. At this time, the tilt error signal is 0. When the amount of light sensed by the two photodetectors is different, the disc is being slanted and the tilt error signal isn't 0. The tilt servo is operated in such a manner that the tilt error signal becomes 0 volt and controls the pickup and disc as being parallel. The tilt error fed into the mechanism control microprocessor is AD converted into units of 5 bits, and a pulse width modulated output representing the error is applied to the tilt motor. At this time, the tilt angle of pickup is varied, with its midpoint being locked. The tilt servo can track tilts that are within plus or minus 2 degrees. If these limits are exceeded, the state of a mechanical switch is detected and the tilt motor is stopped. When playing back a LaserDisc, it is necessary to rotate the disc at the same speed at which the original recording was made. When the rotating speed of the disc is varied, colors may be reproduced incorrectly, images may be distorted, or in the worst case, there will be no picture. For this reason, the TBC servo is used for the correction of the time base during playback. It consists of the spindle servo and the CCD servo. In this video, we will explain the structure, functions, and the operations of these servos until the spindle lock operation is complete. The spindle servo controls the rotational speed of the spindle motor, so that the disc rotates at the same speed at which the master recordings were made. Although there is one spindle motor, there are separate spindle servos for the LaserDisc and the compact disc. In this video, we will explain the servo used during playing back the LaserDiscs. When a disc is set and the play button is pressed, the spindle motor forcibly accelerates the LaserDisc rotational speed until a speed is attained at which the video signal can be demodulated. Until 85% of the regular rotational speed, the RPM of the spindle motor is detected by a motor-mounted frequency generator and controlled. The FG is designed to put out 24 pulses per revolution using a photo interpreter. Then, the video signal can be demodulated and the RPM of the spindle motor is controlled by the reproduced video signal. After the spindle motor is up to speed, the RF signal derived from the pickup is subjected to FM demodulation by the video demodulator. Then the horizontal synchronizing signal contained in the video signal is separated with a synchronization separator. Next, the frequency and phase comparator detects time base errors in the disc's rotational speed by comparing the phase and frequency of the horizontal synchronizing signal deriving from the disc with those of the reference horizontal synchronizing signal generated by a quartz crystal oscillator. With the time base error signal, known as the H error signal, the RPM of the spindle motor is controlled. In addition, the synchronization separator is also responsible for extracting the color burst signal. This signal undergoes phase comparison with the reference color subcarrier in order to generate the burst error signal, which is characterized by an even higher frequency than the H error signal, and it is added to the H error signal. This time base error signal is compensated by the equalizer. The spindle motor operates in a response to low frequency components The CCD servo responds to high-frequency components, which the spindle motor cannot respond to. The servo gain of the time-base error signals for controlling the spindle motor is varied according to the sizes or kinds of the disc, such as CAV and CLV. The gain-controlled error signal is converted into a PWM signal to control the spindle motor. Since the PWM drive uses transistors in their switching operation region, highly efficient control is possible. In a word, the spindle servo controls the RPM of the disc so that the reproduced video signal and the synchronizing signal lock onto the same NTSC standard signal. In the CCD servo, the CCD is used to reduce jitter electrically. These are the high-frequency time-axis variations which occur in the picture signal due to the eccentricity of the disc as well as other factors. An excessive amount of jitter in the picture signal may make it impossible to correctly reproduce color images and badly distort images. The CCD is the delay line, which is variable dilated time, and it can transfer to the subsequent stage one after another for every clock cycle. Increasing the clock frequency decreases the transmission time, while lowering the clock frequency increases the transmission time. Capitalizing on this characteristic, with the time-base error signals, the CCD servo controls the oscillating frequency of VCO by using this error signal and accommodates jitter, which is contained into the reproduced video signal. After the spindle servo has become operative and the frequency of the played back horizontal synchronizing signal has reached the prescribed value, a near-perfect video signal can be obtained, and the picture can be displayed on a TV or monitor screen. The state in which the playback horizontal synchronizing signal gets in phase with the standard horizontal synchronizing video signal is referred to as the locking of the spindle servo. The spindle servo lock detector detects this state. Since nothing but the noise appears on the monitor screen until the CCD servo starts to operate and the spindle servo locks, the CPU squelches the video output to prevent the noise from being output until the spindle lock is detected. Then the reproduced picture is output. We will explain the example of the cooperative operation of each servo unit until the LaserDisc starts playing. First, the disc is set on the tray of the CLD player. After the close button is pressed, the LaserDisc is loaded. When the disc is clamped completely, the lens is moved toward the disc forcibly. The focus servo detects the existence and kind of disc. When the play button is pressed, the pickup is moved to the innermost track. The focus servo starts to operate, and the lens is moved forcibly. Then, the zero cross point is detected, and the focus servo is closed. Next, the spindle motor starts to operate, and the disc starts rotating. The tilt servo, tracking servo, and slider servo is turned on when the disc starts rotating. The misclamp and the size of the disc are also detected during the rotation of the disc and before it reaches 1530 RPM. Once the CCD servo starts to operate, and the rotating speed of the disc has attained, the spindle servo is locked. Then the video squelch is released and the reproduced picture is output. This concludes the structure and functions of CLD Players. We hope that you will continue to read the tuning fork repeatedly in order to broaden your knowledge of CLD Players more and more after you watch this video. For your information, we will explain video signal processing, sound signal processing, and digital TBC in the Video Tuning Fork Part 3. Signal processing of CLD Players.